Guys want to figure out late assignments right now, doing that during the review, much like Jerica on Thursday, probably would not be the most helpful thing to do, despite it helping your grade in the short term. So I would highly recommend that you do it at the end of class, homeroom, something like that to get me those papers. They're not going to be graded until Friday anyway.
I have all of them ready right now.
Okay, great, wonderful. So you can go put it in that large bin that's sitting back there, the large one on the table, and then be done with it. But if you're sorting through stuff, looking through it, I would highly recommend you don't do that right now. Highly recommend. Your choice, you do you. But would highly recommend you don't. So, part 2 is tomorrow. And remember, part 2 is going to have questions that are not necessarily on part 1, right? So just because it wasn't on the quiz on Friday doesn't mean we don't need to go over it. For instance, this was not on the quiz on Friday. So don't think, let's skip it because it wasn't on the quiz. It could be on part 2. Now, with that said, it might not be. Would you like to see it or would you not?
No.
Would anybody like to see part 1? It's totally fine if you want to. Does anybody want to start like the back of the packet and work forward?
Yes.
Is that what we want to do? Okay. So that's what I figured you want to do. We'll start with number 14. All right. So a lot of you guys are like, we've never seen anything like this before. Literally, there are 3 homework assignments you have not turned in to me that have this on it. But that's fine. What kind of center must G be? In center, because it's the center of a circle that is inscribed in the triangle, right? Inscribed, written inside. So we have a circle, and circles always have what? Radii. Anywhere from the center of the circle to the outside of the circle, right, will be a radii. Notice radii are always the same length. That's what a circle is. So F to G would also be a radii. And remember, we measure distance, right, to the side of something at a perpendicular angle, right? We wouldn't measure the distance from G to this side, from here to here, right, or here to here, right? In order to measure distance to something, we measure perpendicular. So if I want to measure from G to this side, I measure at a perpendicular angle. So whenever we have a radii, we're always going to measure perpendicular to the sides. So those are 90. Cool. All right, so a lot of right triangles. So if we have right triangles, we can do Pythag, right? We can also get similar triangles really easily, because if we find a right angle and then another angle that matches, right, then we've got double A. So how about we figure out y? Well, we have 2 right triangles here, so we can do Pythag. We know a leg, and we don't know this leg, and we don't know the hypotenuse. So we at least need 2 of the 3, right? So if we can figure out that hypotenuse, then we can use Pythag to figure out what y is. Well, luckily, this triangle already has its legs figured out, right? So let's do Pythag to find the hypotenuse. Here are our 2 legs. That's our a and b squared. We know this is the hypotenuse because it's across from the 90, right? So that's going to be our c squared. So we have 5 squared plus root 21 squared. And you're probably like, oh my god, he threw roots on here. It actually makes it really easy. You're welcome. Equals whatever this is, this length right here, squared. We'll call that question mark just because I don't want to confuse you. Awesome. So that's just Pythag. Again, the long part, the longest side is the hypotenuse that's across from the 90, and that always goes here. Don't goof that up. If this was a leg, it would go somewhere in here, right? So when we square this stuff, what do we get? Well, we get 25. What's the square root of 21 squared? 21, right? Hooray for roots. And what we get is 46. And then we root both sides, right? And when we root it, we find out that that length over there is root 46, which sounds like a fun place to drive. So this whole length is root 46. Great. You're probably like, oh, that's gross. It's fine. We're going to use it to find y, which will be a nice number, because when we square this, it becomes 46, right? Is everybody cool with that first part? What's the question?
You said that the hypotenuse leg is across from the
Yep, here's the 90. There's the hypotenuse.
the one on the other side.
Yeah, so that's the hypotenuse for this guy too.
So they're the same.
They'll use the same hypotenuse, yeah. They share that side, right? Now, and you're right, they will be the same. So Michaela realized really quickly we don't have to do a lot of work to figure out why, right? These 2 triangles are congruent. How do we know? Side, angle, side. Side, angle, should be this side. Actually, let's use HL. So hypotenuse and leg, right? They match here and here. Hypotenuse and leg match here. So these guys are going to match. You could set it up. 5 squared plus y squared equals root 46 squared. And you'd figure out that y squared would be root 21. So this is root 21. They're just two congruent triangles. You could do angle side. Well, I guess you could do angle side angle because we don't have this side. But you could do HL, right? Or just set it up and do Pythag. Same thing. So, to figure out x, well, x is part of a right triangle, so we can do Pythag to figure it out, right? But unfortunately, we have a leg, we don't know this leg, and we don't know the hypotenuse. So once again, we need to figure out the hypotenuse so we can figure out what this is. Luckily, we have another triangle down here that uses that side, right? And it's a right triangle. So we do Pythag to figure that out. Yeah.
Couldn't you do angle and
You could, but you don't need to. You can just do Pythag. You could also, I mean, I guess you could set it up this way and say, because they both share angles, you could say 5 is to 5 as 12 is to x. Well, x is also going to be 12, right? Yeah, so you could do that. Or you could do Pythag. I think that's what most people do. 5 squared plus 12 squared equals we don't know squared, right? That's 25 plus 144. What is that? 25 plus 144? 169. What's the root of 169? 13. Well, it's a funny number. Nice. So if this is 5, 12, and 13, and this is 5 and 13, that's got to be the 12, right? Oh, sorry. My desk is high up, so I have to go back and forth. All right, so, yep, x is 12. Really difficult or not so difficult once you see it? Well, because these two triangles are congruent, 5, 12, 13, right? That's going to be 5, 12, 13. Or maybe you don't see congruent, you can just do math and do Pythag, right? So 5 squared plus 12 squared, we got that 13, right? And then we do 5 squared plus we don't know squared, right? They're both legs, equals 13 squared for the hypotenuse. You don't have to.
like, is that something that we use to figure it out?
You could, yeah,
You don't have
because they're congruent.
to explain it.
Mm-mm.
I know you don't
No.
have to explain it, but is it what we use?
Yeah, I mean, basically, right? Yep, it's just with numbers. So lots of ways to do it. Like Bailey used similar triangles. That was really clever. Pythag, when in doubt. Right angles, Pythag. 13. How many triangles do you see? 2. Big guy, small guy. We're going to use similar triangles to figure out these different parts. So just so we're clear, how long is the side here for the big triangle? 12, thank you. Awesome. So let's compare small to big. Small side is 9, right? And big side is 12. So their relationship, right, will be the same as, let's do 12 and y. 12 on the small triangle, right? We got 9 on this guy, 12 on this guy. And then we have the small side here, 12. We'll go with y. I'm going to do that again because you guys are busy writing down and taking forever to write 4 numbers. So look here, look here. Small side goes with large side, right? We know this to be true because these angles are the same, right? And then these guys are the same. Let me flip this around. These angles are the same, sorry. And these angles are the same, right? So we have angle, angle. We also have a shared angle at the top. Cool. So we know this side on the big triangle is going to go with this side in the small triangle. I wrote that. I started with the small going to big. So I go with small here, going to big. So 12 goes to y, right? Let's solve. Well, how do you solve a problem like Maria? Well, putting the variable on top is always a good step. So I'm going to multiply by 12. I get 144 over 9 equals y. And if you don't know what that is, it's 16. So y is 16. Clever way to figure that out is don't write 144. It's 12 times 12 divided by 9. That's just dividing by 3 twice. I'll divide that one by 3, and I'll divide that one by 3. And I get 4 times 4, which is 16. That's kind of clever, I think. All right, how do we figure out x? Well, x is the small triangle side, right? And how long is this side here? Oh, sorry. How long is this whole side here? X plus 5. Thank you, angle addition postulate. So that looks gross, but we can figure it out. Let's use 9 and 12 again. So I'm going to write that 9 over 12 equals x over x plus 5. Nope. Is that part of a triangle? Nope. So small side is x. Big side is x plus 5. Cool? Just like we did 9 and 9 plus 3. Is that okay? Okay. So now we just multiply over. Remember when we do so, we wrap it in parentheses because there's two terms. And then we do distribution. And this is all recorded, guys, so if you want to watch this later, you can. You'll probably be better off just watching now, but it's up to you. So x is 15. I just did distribution, and then I got my x's together. Terrible idea in real life, great idea in math. I put these on here because they're actually a lot easier than the proofs. They are. So I was trying to be nice. I didn't put a lot on the quiz, part 1 or part 2. But I put them on there because I thought you might enjoy them as a grade boost. When I set the bar low, you guys tend to trip over it, though. So, I don't know. You win some, you lose some. How do we feel about this one? Similar triangles, CSP, essentially, is what we're doing, right? Okay. When in doubt, you can write the triangle similarity statement, right? And get your letters matched up, and that'll tell you what matches up here. If you're not sure what goes with what. Like, for instance, we know triangle AED, because of the angles and how they match up. A is going to go with what on the big triangle? A, because they share that angle. E is going to go with what on the big triangle? C, and D is going to go with, and then we can use that to match things up. AE goes with AC. AE is 9. AC is 12, right? Are you seeing what I'm saying here? Right? That can help you if you get lost. Yeah.
What does knowing similar angles help you do, or congruent angles help you with what we did?
Well, we know they're similar triangles because they're angle-angle, right? And so that allows us to set up this proportion, right? That's why we know it works. And also it helps us match up what goes with what. So if you get lost, you can figure out what goes with what. Spoilers, if the triangles are inside each other, the sides that are connected are going to go together, right? But that's why. 12, what kind of lines are those? Perpendiculars, otherwise known as what? Orthogonals. So we have lots of right triangles. And remember, orthogonals, they create similar triangles, right? So we should be looking for similar triangles. For instance, these two triangles will be similar. Why? Vertical angles here and here. So by angle, they're similar. Well, great. Let's match them up. First of all, how can we figure out V? Pythag, right? Yeah. Now, is V the hypotenuse or a leg? It's a leg. So when I set it up, it's going to be one of my A's or B's. So it's going to be 3 squared plus V squared equals 5 squared, right? 5 is the hypotenuse. Don't screw that up. Don't put the 5 here and the V over here. It's a 3, 4, 5 right triangle. So if you know your special right triangles, super easy. V is 4. All right, now let's figure out what x is. They're similar, so let's match up their sides, right? So if you look, this side right here is between the red and the green. If you want to write the triangle similarity statement to figure out what sides go with what, right, to match up the letters, that's fine, like I did here, right? And then set it up that way, that's fine. I'm going to just do it in my head real quick. See how 3 is between the red and the green? So it's going to go between red and green on this one. So 3 is going to go with what number on this triangle? 7, very good. So 3 on the small triangle, 7 on the big. Now x on the big is between the green and the unknown, right? So green and unknown, what's green and unknown on this triangle? 5. Now can we solve a problem like Maria? We can, right? One variable. I'm going to flip both. That way x is on top and make it easier on myself. X is 35 over 3. Sometimes they're gross. There's only so many numbers that work with right triangles that are nice. That's why 3, 4, 5 is really special. All right, now how do we figure out y and z? Well, this is a bit of a tougher problem but all we need are those two triangles. Do you see how they're inside each other, right? Small triangle, big triangle, right? So they're going to be similar. They have a shared angle A. So if you need help, angle A is shared, which means what color should this angle be down here, angle C? Green, right? Because it's red, green, blue, red, green, colors are hard, red, green, blue. So that might help you match stuff up. So let's go big to small. Let's write Y. Y is between what two color angles? Red and green. So what's between red and green and the small triangle? 3, right? And they're similar. Now we need some solid numbers, right? So I wouldn't want to put Z in here necessarily, but I'll write it down. Z is between what two angle colors in the big guy? Green and blue. What's between green and blue over here? Try again. 5. Green and blue, right? All right, so we can't solve a problem like that, so we need to go get the other one. So between red and blue we haven't done yet. What's the distance between red and blue? 12, thank you. And what's that going to go with, red and blue and the other triangle? Try again. 4. Between red and blue is 4. Again, you could write the triangle similarity statement and then match them up using CSP.
How do you know which red and blue?
Well, we're looking at two triangles, right? And they're similar by double angle, right? Because they share this angle. So right angle, blue angle, right angle, blue angle. They're similar, right? And so we're looking at these two. And then matching up their sides. Do you know how we match up their sides? You can either do it by angle color or you can write the triangle similarity statement. You could write that triangle AGE is similar to triangle, well, it's going to be A in the big triangle too, right? G is the green angle. What does it go with on the big triangle? Yep, so C. And E is going to go with D, right? So you can do CSP to figure this out. AG and AC will go together. AG is 5. AC is 4 plus Z, right? Ooh, that's a good point. Guys, we missed out. So it's not Z that it goes with. It's this whole side here. So that's 4 plus Z. My bad. 4 plus Z. Do we see that? I'll be more clear. Also, I won't give you as many variables on one problem. I just don't like making lots of these diagrams because they're hard to make. So when I make one, I utilize it a lot. Okay? Well, we go the whole side of this triangle, right? And that's Z plus 4. It's hard to see, and I'm sorry for that. You won't have something like that in your quiz. Okay? Something where you have a lot of things to look at. It'll just be a few. I just wanted to give you lots of examples. The whole side is Z plus 4, right? That was my bad. I saw the Z there and thought it meant the whole thing, but it's not. It's Z plus 4. So let's solve for Y first. So I'm going to take the ones that I know and solve. What's 12 divided by 4? 3. So Y must be 9. Right? So I'll use 12 over 4 again and find out Z plus 4 over 5. Well, that's 3. Whoops. Times by 5 and subtract 4. Z is 11. Again, I won't try to give you lots of variables on one problem. I'll try to keep it at most 2. I just don't like drawing lots of diagrams, right? I could have done the exact same diagram or a similar diagram multiple times and had different questions, right? But I didn't want to do that. Lots more paper, really hard to draw. Microsoft Word is not nice. So I just put a lot on one diagram. And I'm sorry about that, but it do be like that sometimes. Again, similar triangles, PFAG, right? Ready to look at 11? All right. What kind of lines are those? Also, we did these in reverse, so they get easier as we go. Sorry. Right? They're medians, right? What?
Because like if I understand the hypotenuse.
I guess, yeah. So they're medians. What special properties do we know about medians? First of all, they're midpoint to what? Vertex. So these are midpoint to vertex. So this is a midpoint, right? And that's got to be a midpoint. And this has to be a midpoint. Right?
And they have a 3-to-1 ratio.
They do. So if this is 5, that's the smaller side, right? What's x? Thank you. Yeah. You don't have to prove it. We know that's a true thing about it. We can prove it if we have to. The applications of this is really easy. That's why I threw it on the test. Don't trip over the low bar. If this is 6.5, what's y going to be? 13.
So this is literally, we don't have
No, it's just, you know it's true. I didn't ask you to prove it. You're using the properties. Okay?
Oh, that's it.
Okay, now we have to find z. Now this is a bit harder. It might help if you write this in. This one takes a big brain play.
Yeah, I don't have that. So we can try. I have that for one day.
What do you see?
The 13.5 and then the other one can be.
If it was a right angle, we could do it.
Wait, shoot, but there's a little isosceles.
Ah, yeah. Guys, isn't it true? Isn't it true if a point is equidistant from the endpoints of a segment that it must be on the perpendicular bisector?
I do not know how you got the isosceles triangle.
Both are 13. Converse, or actually not even converse, straight up isosceles triangle theorem.
Wait,
Right.
does that mean that we have a hypotenuse?
We do. So check it out. Check it out. Guys, if a point is equidistant from the endpoints of a segment, then it must be on the perpendicular bisector, right? Remember perpendicular bisector theorem? So that means this is a perpendicular bisector because it's already the bisector. So it must be the perpendicular bisector. So now we have a right angle triangle, and then Shelby's right. Pythag, 12. And 12. What's z?
24. Yeah, can we go through these six?
So Shelby knows her special right triangles from remembering earlier. 5 squared plus we don't know squared, whoops, equals 13 squared, right? 13 is the hypotenuse. 25, 169, you subtract them, you get 144, the root is 12. New root. 5, 12, 13 is a special right triangle, just like 3, 4, 5. Hypotenuse leg. So do you see how this triangle and this triangle both have the same hypotenuse? Do you see how both of them have the same leg? Then they're congruent by hypotenuse leg. Do you see how both of these have the same angle? They have the same side and they have the same angle? Then they're congruent by a angle side angle. That's how it works, guys. That's how it works. Quiz 1. You should retake that this week if you bombed it the first time. It's a joke. Please take quiz 1 again. I beg you. Here's 2 triangles. They have 2 angles the same and a side in between. Are they congruent? Yes. Write the congruency statement.
I still haven't retaken quiz.
Oh, you saw vertical angles? Great. Here's some free points. No, no time. Don't care. All right. You guys want to see 10? You do? Are you sure? That's thick triangle. All right, cool. So first thing we're going to do is we're going to create some parallel lines, right? We're going to make this a medial triangle of a bigger triangle. So let's use some colors. How about this color? I'm going to do a parallel line here that's parallel to this.
Okay, wait, why is that?
Well, we're going to make this the medial triangle of a bigger one. Remember the medial is this guy? So if you have a triangle, right?
So
We're creating
the
this.
whole point is to make this elbow lower?
Yes, exactly, Triforce. So the OG triangle will be this black triangle essentially, right? So we're going to create a bigger triangle around it by creating parallel lines. So these guys are going to be parallel. And we're going to make a line parallel to this guy. So that's like this. Oh, no, it's not. Sorry. It's more like that. My bad. My bad. Hey, look, I'm you guys. All right. Let me reiterate. Hey, look, I'm you guys. All right. Where's my shirt that says Savage? Okay.
What?
Seriously. I was promised that by my Newark kids like 6 years ago. They're like, we have to get them a shirt that says that because it's true, and they never did. Newark. Newark. Teaching Newark, Illinois. All right, so look, we made a big triangle. And we're going to say that this is parallel to this. And this is parallel to this. You think my drawings are ugly? You should see yours. I mean, this one's bad because I'm trying to do it quickly, but still. All right, and then we also know, or actually, let's put some dots on here and call them something. All right, ladies, I need you to focus because I'm going to go through this quickly, and you're going to be like, wait, which is fine as long as you're trying. All right, so we're going to say I created line DCE, right? That yellow line. And I made it parallel to what other line? AB. Again, would not recommend you drawing this. You've drawn it like 3 times already now. Go practice drawing it at home. I made this blue line, EBF. And I'm making it parallel to what? Very good. And I made the pink line, which is DAF, DAF. And I made it parallel to? BC. Letters are hard. All right, so that's the first half that I'm going to give you 3 points for.
3 points for just that?
Yeah. Again, I try to make it so the easy stuff is worth more points. That way you get a better grade, because that's kind of the heart of the problem, right? It should be worth more. Understanding that you can do this. It should be worth more points. But the problem is I set it up, and then you trip over it. The bar was so low, you tripped out. Yeah, okay. I'm shutting up now and moving on. All right, so this stuff, right? We know that as well. This is by Medial triangle theorem. If you want, you can abbreviate that by doing this Triforce symbol. Medial triangle theorem, okay? We know that all these segments are congruent. So AC is congruent to BE, is congruent to BF. Okay? You're not going to do this on your quiz because you want more points, but I'm going to do ... meaning continue. This is called an ellipses. Not ... but you're going to keep calling it that. Oh my God, he said ... Worse than leaving me unread. You'll write the same thing, but for all the other segments.
If you just write the dots, will you still get one?
No!
So what do you write? Can you write
Are you trying to copy this down? Is that why you're trying to write it? Because that seems like a waste of your time. But you know what? I'll write it all out, and then you'll copy it down, and you'll have learned nothing more than if you had just watched.
Wait, so but we have to write this out.
Yep, because you want free points. If you could do ... I would only give you 1 point.
But then you didn't elaborate. You said don't write that.
All the pink ones are congruent. It's what I put on the diagram. All the yellow ones are congruent. All the blue ones are congruent. That is exactly what that is. You're welcome. You're welcome. No, it's all good. It's all good. It's all good. All right, so I'm just trying to thread a needle of people that want me to speed up and people that want me to slow down because they're like, oh my God, right? And it's difficult. So bear with me. All right, so now that we know that, doesn't that mean A, B, and C are the midpoints of the big triangle? Yep. Which means we can draw some perpendicular bisectors here, right? So I'm going to draw a line right here and say it's the perpendicular bisector of this side. Again, notice my phrasing. The line I drew is the perpendicular bisector of side DCE. It is perpendicular to this side. Are we cool with that? So I'm going to write that. So again, letting there be, let the line that I drew, which I will name later, because I'm going to have to put some points in, right? There's going to be an intersection point. Let this be the perpendicular bisector. That's the symbol for perpendicular bisector of what side? What side is it the perpendicular bisector of? DCE. Good. Now, I'm going to do that for all of the sides. And then what I'm going to do, and it might be easier to do this as you go. The reason I did this is because that creates a transversal, right? These are parallel. That's a transversal. So we have alternate interior angles here, right? Right here. And here. Do we see that? Alternate interior in the inside of the parallels, opposite sides of the transversal. Are you digging that, Shelby?
Yes.
Okay. So then I'm going to do by alternate interior angles theorem. Angle this is congruent to angle that. Now I'm going to fill that in later. Actually, let's fill it in now. Okay. So notice I need letters EC what, right? I can't even call that angle. So just so you see that before my diagram gets too crazy, that's what I'm going to do for all the sides. Are we cool with that? I'm going to draw a perpendicular bisector for this side, and then I'm going to get alternate interior. I'm going to draw a perpendicular bisector for this side, right? And then I'm going to draw alternate interior. I'm going to do it for this side and get alternate interior. Okay? So let's draw it for the purple side. There's my perpendicular bisector. And it's going to make alternate interior with this. Are we seeing that? Right? Two parallels, transversal. The better you make your parallels, the easier it will be to actually see this. And then I'm going to draw a perpendicular bisector from here. Spoilers, guys, my lines are really awful. This is a perpendicular bisector, trust me. This is 90. This is totally 90. Totally 90. My lines are really bad. And then alternate interior here. Are you seeing that? Inside the parallel. Inside the parallels. These are parallel. I know they don't look parallel.
Why are those on the other side? Yeah, shouldn't the boxes be on the other side?
Oh, sure, sure. That works. That works. Yep, I guess so. They're still both 90, but just so you're clear. Yeah.
Like the pink one.
What?
Like right here.
No, we're all good. Pink, these go together. That's why I was trying to do this in real time, which is why I don't want you watching, because then you're going to get confused. Or I don't want you writing, because you're going to get confused. These go together, these go together, these go together. Better? If you see it in real time, you can see what goes together.
Oh, I thought that was
Yep. All right, so where they intersect, I'm going to call that point K, and then I'm going to label all these points. So C, next letter is G. Then I have H, but I'm going to skip that. I, going to skip it, call that J. I already used K, and I'm going to call this L. So again, just getting all these points here because these are going to be orthogonals, right? And that's how I win. And this is how I win, right? Okay, so what line is perpendicular bisector to DCE? CKG, thank you. What line is the perpendicular bisector to DAF? JKA, thank you. With her special eyes. All right, and then what is the perpendicular bisector to EBF?
LKB, DKL.
BKL.
I'm kidding. You know, you just.
All right, and then I match up my angles. All right, so looks like angle ECG is congruent. ECG went with what other angle? This angle went with what? Try again. AGK. Right, these two are alternate interior. AGK. And then let's do this one. DAK. And angle. Whoops, letters are hard. DAK is going to go with angle. That's DAK right here, right? What does it go with? DAK, this one right here, is alternate to this one. So BJK.
Can you say CJK too?
Yeah, CJK would. Well, actually, CJK wouldn't be alternate interior. It's on the same side. Got her. Revenge. All right. And then we did DAK. We did this one. We did this one. Let's do this one now. So that's angle, looks like angle EBK, and it's totally a right angle. It's totally a right angle. EBK, that one goes with what? Very good. Now, I'm going to highlight this. You don't need to do this. But this is an orthogonal of our original triangle, right? Vertex to 90. This is an orthogonal, vertex to 90. And this is an orthogonal. And look, they all intersect at K. So therefore, the orthogonals of triangle ABC are concurrent because they all intersect at K. So what we do is we find the perpendicular bisectors of the big triangle, and they create our orthogonals automatically of the small triangle. And we win.
About how many points with that question? 25.
13.
Enough to break my grade.
You need to stop crying, okay?
Hey, I'm not proud of you.
Okay, shut up. So, 3 points right there. Create parallel lines. Then the next thing. Say what things are congruent. That's half the problem. Stop crying.
How much is that?
I'm gonna cry because you say mean things.
Half the problem. You guys need a kick in the ass today. I'm sorry, you do. Then you draw your perpendicular bisectors.
Okay,
It's not hard. You just need to break it down. It's like when your room's really messy, don't try to clean it all at once. Focus on an area and then be done. And then we do alternate interior angles, because of course we do. And then you write what they gave you. It's 4 major things. Is it a lot of writing? Is it alphabet soup? Sure. Letters are hard, guys. But like the proof is not. Draw a big triangle with parallels. Get things congruent by medial triangle theorem. You can even use a symbol if you don't remember the name of that theorem. Draw your perpendicular bisectors, because of course you do that in this problem. And then alternate interior angles.
Wait, that's like for the medial triangle theorems?
Mm-hmm.
Like, are those the line segments?
Yeah, it's saying, right, when you have a medial triangle, then you know that these guys will be congruent, right? And so on and so forth.
Oh, so it's
Right, and it's because those are parallel.
So it's every little.
Mm-hmm. That's it, right? Because those are parallel, we have a medial triangle. It connects all the midpoints. This can be a really easy problem, actually.
And then the perpendicular bisectors, they're just for the little triangle in the middle. They're just for like.
Well, they're for the big guy, right? And then that naturally creates the orthogonals of the small guy.
But they come from the smaller, like the angles that we use.
They come from the midpoints of the big guy because they're perpendicular
Yeah,
bisectors.
They're also like the angles of the small triangle, is what I'm saying.
Yes,
Okay.
because orthogonal, vertex to 90. Don't think of it as the angle because it's not cutting any angles in half or anything. It's just vertex to 90, right?
Well, I know, but like if they're the vertex of the small triangle.
Do you want to see 9?
No.
Perpendicular bisectors? Yes, no, maybe? Yes? Okay. So let's draw some perpendicular bisectors. For this one, it's weird. You only draw 2 of them, and you're going to prove the third one has to be concurrent, okay? These are not Sevians, right? Because they don't go from a vertex to the opposite side, right? They go from a midpoint to just wherever they go, right? No. That's Sivas theorem's converse. That's it. Right? So when you draw your perpendicular bisectors, are they Sevians? No. Why not? They don't go to the vertex. Very rarely will they, right? Only in an isosceles triangle or an equilateral. So we don't assume that. So are we going to use Sivas theorem? No, because they're not Cevians, right? So we're going to do something else. We're going to draw two of these, and we're going to prove the third one has to go through K, right? It's not weird that two lines intersect at a point. We can assume that, right? They're going to intersect at some point. They ain't parallel. No way. So they're going to intersect at some point, and then we're going to prove the last one has to go through that point too. So let's call this D, and let's call this E, and F and G or something, okay? So we're going to say let DKG be the perpendicular bisector of what side? What side is DKG the perpendicular bisector of? CDA or ADC, same thing. And then we're also going to create EKF and have it be the perpendicular bisector of what side? BEC, same thing. Yep. Cool. And we know they intersect at K because they share that point, right? So now we're going to prove the last one has to intersect at K. And the way we're going to do this is we're going to use perpendicular bisector theorem and perpendicular bisector theorem converse, right? Because we're talking about perpendicular bisectors. Now, the theorem says that if it's on the perpendicular bisector, which K is, right? K is on this perpendicular bisector. That means it's equidistant from the points, right? So I know this. Okay? Well, isn't K also on this guy's perpendicular bisector? So he's going to be equidistant from those two endpoints. So that's by perpendicular bisector theorem. AK, BK, and CK are congruent, those segments I drew in. Now, by the converse of the perpendicular bisector theorem, if K is equidistant from B and A, if K is equidistant from B and A, doesn't that mean that K is on BA's perpendicular bisector? Right? If it's equidistant from the sides, it must be on this guy's perpendicular bisector. Well, if it's on this guy's perpendicular bisector, and it's already on the other two, they're concurrent. So by perpendicular bisector theorem converse, K is on whose perpendicular bisector? What side's perpendicular bisector? Well, we already know it's on this one, and we already know it's on this one. We're proving it's on this last one because it's equidistant. So what side? AB. On AB's perpendicular bisector. A.
No.
A.
No. Before that.
Down. No, but down.
Down. It says
The bottom
blank
layer
is on a B.
K.
K.
Okay, well, it looks like U.
Why would my U be so tall?
I don't
U's
know.
look like
Why
that.
would your K be so
That's a U.
circular?
K. That's a K.
Your K's are not concurrent.
You guys are all big dummies. Therefore,
Okay, well, it just doesn't look like a K.
the perpendicular bisectors of triangle ABC. Also, I'm writing quickly because you guys want to get through this really quickly, right?
Well, I'm not saying that. Like, I just was wondering. You attacked me. Call me dummy.
Well, that wasn't an attack. It's just a fact. Yeah. Like, if facts were attacking, then Scholastic Bowl would be the greatest case of assault ever.
They lost.
Excuse me, Judge, I have been assaulted. They got a question right.
Judge.
All right. The proof by contradiction one. I did it in the review. This one's the proof by contradiction, which makes sense because we assume the opposite in the diagram, didn't we? We assume they're not concurrent. Then we say, then there must be a line that is concurrent, right?
Oh, they're Cevians. I see them.
And then that means because this is concurrent by Siva's theorem, AJ over BJ over B times BE over CE, et cetera, that should equal 1 by Sieve's theorem, right? If we go around the triangle. And then move. You can put them away at the end of class, okay? So, but we're also told that this over this times this over this all the way around equals 1.
So we're given that.
Yeah, we are. Don't forget that we're given that. So this, A over B times C over D times E over F, should equal A over J times B over J, et cetera, et cetera. But that's a contradiction, because everything cancels except for A over J over B over J equals AD over BD. And how can we have this fraction equal this fraction? You can't. Proof by contradiction. Therefore, our assumption is false, and the segments are concurrent.
Am I allowed to come in tomorrow in the morning and do my quiz or not?
Yes. Yes, you can.
I don't feel like I'm gonna finish my
Can I see if I can come in here this hour?
Yeah, of course.
Am
I can't let you take the quiz, though, because I reviewed with you today. Does that make sense?
Yeah, I just needed more reviews.
Okay, that's fine. Yeah, that's totally fine, Cheyenne. How are you today? Just okay?
Yeah.
Okay, well, okay is a good place to be sometimes. Here you go. Mm-hmm.